Let us consider next numerical. You can read the question from your screen. As you can see from the question, we are given with a charge which is deposited on the surface, on the disk of radius 4.5 meter. And this circular disk is present in the z equal to 0 plane. In the question, we are given with rho s, the surface charge density, and we are supposed to find the total charge contained by this disk. Now, my dear, in one of my previous lectures, I have talked about the charge distributions. Do you remember? Charge can be deposited over the line. It can be deposited over the surface or volume. So we can have line charge, surface charge, or volume charge. In surface charge, the charge is deposited over the surface. And in such case, we can define a surface charge density. My dear, it is very simple. Surface charge density is total charge upon total area on which it is deposited. So rho s equal to charge upon area. Very simple. Let us say, for example, I have taken 5 coulomb of charge and deposited over the surface whose area is 5 meters square. So what would be my surface charge density? It is very simple. Rho s equal to charge upon area, 5 by 5. That is 1 coulomb per meter square. Let us consider one more simple question again. Let us say we are given with the surface whose charge density is already given. Let us say rho s equal to 2 coulomb per meter square is already given. And we are supposed to find the total charge contained by the surface of area 5 meters square. So once again formula will be same. Surface charge density rho s equal to charge upon area. So total charge will be equal to rho s into given area. So total charge will be 2 into 5, that is 10 coulomb. Isn't this very simple? But my dear, you cannot expect such simple questions every time. For example, consider our present question. In the question, you can clearly see rho s is not a constant. It is a function. And my dear, whenever there is an involvement of functions, we have to use the method of integration. Are you getting my point? Now, you are very much familiar with the method of integration. In the last lecture of line integrations also, I have talked about the method of integration. It is very simple. What we will do, we will find the infinitesimal charge. In the first step, we will find very small infinitesimal charge by considering very small or infinitesimal area from the given surface. And then we will integrate this function over the complete surface, over the complete area with proper limits to get the required charge. Isn't this very simple? So in other words, to get the complete charge, we have to solve this integration. Integration, well, of course it would be surface integration, rho s ds. So let us solve this integration. Rho s is the surface charge density as it is given in the question. ds is the differential surface which is required to calculate the surface integration, as you already know. Now, my dear, in this context, point out very important thing over here. We already know that ds or differential surface is a vector quantity, isn't it? But we are treating it as a scalar quantity in our answer. Can you guess why? My dear, the reason is very simple. We are trying to calculate the charge. We are trying to integrate the charge density, which is a scalar function. Charge or charge density is a scalar. And to integrate such scalar function, we also need the scalar differential, the scalar ds. And hence, rather than writing vector form, we are taking ds in scalar form. My dear, the scalar form of ds is not very much different from the vector form. It is exactly the same as we have seen. But without unit vectors. That's all. ds and ds vector, they are exactly same but without unit vectors. So let us write differential surface or ds for our question. Now you also know that we write the ds from the expression of dl, differential length, isn't it? So let us recall the expression for dl. It is as you can see from the screen. My dear, we have to use the dl from the cylindrical coordinates because our question is in cylindrical coordinates. You can easily see the variable is rho. So this is our dl. We can also do one thing. We can skip the unit vectors. As I just explained, we are going to write the ds in scalar form. So we will not be needing the unit vectors. So our dl will be, as you can see from the screen, that is d rho, rho d phi plus dz. Now let us write the ds for our given surface. Once again I remind you, for writing ds we see the surface, and for the surface we have one coordinate constant. We skip that differential and rest two are variables. We multiply that differentials, isn't it? So look at our question. We are given with a disk which is present in the z equal to 0 plane. That means for our given surface, coordinate z is going to be constant at z equal to 0. So z is constant, rho and phi, they are changing, they are variables. So our differential surface ds will be, as you can see from the screen, very simple. That is rho d phi. So our integration becomes, as you can see from the screen. So we have to integrate with respect to rho and phi. So let us deduce the limits of the integrations for these variables. Now, my dear, I have covered almost each and every detail of the cylindrical coordinate systems in previous lectures, isn't it? So just recall the definition of rho and phi. What is rho? It is the lateral perpendicular distance of the point from the z-axis, or it is the radius of the hypothetical cylinder that is assumed to be passing through the point. Am I right? And what is phi? Phi is the angle made by the rho of the given point or the plane containing the given point with positive x-axis. Am I right? My dear, it is very important to write the limits properly because we have just done our step number 1 in the solution. What we have done in step number 1? We have found the infinitesimal value of the function. In this question, we are supposed to find out the charge. The function is charge. So we have found out the very small value of the charge, infinitesimal value of the charge, dq, by considering the very small or differential surface from the given disk, from the given surface. So we have completed only step number 1. Now, in step number 2, we have to cover all such small surfaces. We have to cover all such ds to cover the complete disk, to cover the complete surface that is given in the question. And this can be done by providing proper limits to cover the disk, to cover the surface. Now let us consider for the rho. Now this is our disk or the given circular charge surface in the question. Now we have to cover each and every ds that is present on this disk, or in other words, we have to cover each and every point that is present on this circular surface. So let us say ds is over there, so rho will be like this. Let us say ds is present like this, then rho will be, as you can see from the screen. So what I'm trying to say, for each point on the disk, for every point on the disk, we will have different values of rho. But as you can clearly see from the diagram, to cover the complete disk, to cover the complete circular surface, rho can take value from 0 to maximum 4.5. So the limits for the rho will be 0 to 4.5. My dear, alternatively, this can also be done like this. The radius of the given circular surface is 4.5. So to cover the complete circular surface, to cover the complete disk, we have to move from 0 to 4.5. So the limits will be 0 to 4.5. Isn't this very simple? Now let us consider for phi. Once again, let us say ds is present over like this. So phi, as you can see from the diagram, let us say the ds is like this. So phi will be like this. So once again, for different point on the disk, for different point of ds on the circular surface, we will have different values of the phi, as you can see from the diagram. You also know that from the knowledge of cylindrical coordinates, we take the value of phi in anti-clockwise direction. So you can clearly see from the diagram, to cover the complete disk, phi can take value from 0 to maximum 360 degree or 0 to 2 pi. So range for phi or limits of the integration for phi will be from 0 to 2 pi. My dear, this can also be done instantly if you remember the fact from the cylindrical coordinate systems. The range for the phi to cover the complete circle is 0 to 2 pi. And here we are covering all the disk, that means our complete circle. So of course the range for phi will be from 0 to 2 pi. So this is how we can get the limits for rho and phi. Rho is from 0 to 4.5, phi is from 0 to 2 pi. So putting everything together, our integration become like this, which is once again a variable separable form, as I have explained you in the previous question. This integration can very easily be solved by the knowledge of mathematics, and the final answer can be concluded.